All right. Just as I started talking, the fan kicks on. Nice. I wanted to review. I'm not sure how quickly I'll review this, but just to give you the purpose of this video is to give you kind of insight into how I view bioenergetics, and which is kind of the fundamental aspect of, I'll say, macronutrient metabolism. Obviously, protein metabolism is a little bit different when you look at it specifically as uh, tissue accretion or catabolism or anabolism or catabolism. However, it's dependent upon energy availability. And so this is just kind of getting into a general overview. We'll see how much depth we need to go into. But just to give I don't want to say, this is going to be my view. I don't want to say a bird's eye view or whatever. The view perspective is relative. So anyway, there we go. So with bioenergetics, basically it's biological energy production. On this note, when you hear this, I'm going to try to incorporate social media perspectives as we go. You may hear people say, well, we don't eat calories. It's like, well, sort of. I understand the perspective on that. We'll get more into that later in the semester. But for now, proteins, carbohydrates, fats, and alcohols are caloric containing. And so if you ingest any of those, you will ingest calories. So just kind of bear that in mind. And we can debate like erythritol, xylitol, the sugar alcohols, which, we can debate their caloric content, but this is basically disaccharides. Ethanol is malted beverages, spirits, distilled beverages. So basically the standard macronutrients. So just kind of bear that in mind. So energy, ATP, hope this is a review, adenosine triphosphates. The pathways are always on. So whether it's your catabolic, anabolic, there's our body's trying to reach homeostasis as much as it can. And so it's, if you're in a high state of energy need and energy demand that is sprinting, it will divert the neurological mechanisms to be catabolic, to produce energy, to do work, and put off anabolism and storing, depending upon the level of intensity and those types of things, or the duration, availability of fuel, etc. So kind of bear that in mind. So it's the homeostatic issue is the body's always trying to find balance. It will shift out of balance for a period of time, but this is why rest is needed at some point to be able to get homeostasis back in check. And so whether that's mental energy and you get tired, you can only stay awake for so long, you can only do so much work for so long. The Navy SEALs are a great example of a group of people who, especially the training, from what I understand, from what I've seen, of just stressing these systems to almost the human capacity, at least for most people. It's beyond because people drop out, they ring the bell. So just FYI. There is a switch. I'll call it a switch, not really a switch because it's not really binary, but it's how we're going to use the fuel that's being used. And so you have a quadricep. It will have fast twitch, slow twitch, in between twitch fibers. And so we can use oxidative metabolism, anaerobic metabolism at the same time, because there may be a tissue that's activated that doesn't have mitochondria, one that does. And so you'll be doing both. Also, the heart, hopefully, never stops during exercise or sport. The brain is always functioning. And so what we also need to realize is there are other non-working, as far as producing force, tissues, at least to do the sport, that are going on at the same time. And so it's just because we have a work output that relies on glycolysis or high rates of, which we'll get to here shortly, high rates of ATP synthesis, it does not mean that there's not mitochondria working. Even in powerlifters, Olympic powerlifters who hate mitochondria, they still have some oxidative metabolism going on. I would say at it's a smaller percent, much smaller percent than others, but it's still present. So part of this is under endocrine control, and so that means carbohydrates, for example, it's I guess triglyceride. Oh, I guess all of them are kind of insulin sensitive to an extent. For example, carbohydrates, you drink or eat carbohydrates, insulin will be secreted, which will try to lessen. This is at rest. Try to lessen the amount of carbohydrates in the blood. This process will also preferentially signal to the muscle to decrease fat oxidation and increase glycolysis. You could still be using aerobic means. It's just how, we'll get to this in a minute, how substrate gets to the quote unquote Krebs cycle, TCA cycle, citric acid cycle, all the same thing. Sorry, it's confusing. But whether it's beta oxidation for fat oxidation or glycolysis for carbohydrate, getting to that cycle is regulated partially by insulin, depending upon the presence of it, which in essence, it's driving carbohydrate in. And so the concentration within the muscle cell, the working cell, will switch to have higher concentrations of glucose, glycogen. That's the preferred substrate. In essence, you get more ATP more quickly. This is the issue with the ketogenic carnivore diets. We'll get to that when we get to diets. But just to touch on this as far as the endocrine control, then you have exercise and nutritional control. So we burn what we eat. That's the nutritional part. And the type of exercise, the intensity will determine also which substrate or fuel is used. And then we can adapt, we can train. And so we'll get to that. So that's, talked about powerlifters, endurance athletes. They're at the opposite ends of that training adaptation. And so they're able to use either they've generated a lot of mitochondria, or they've prevented a lot of mitochondria from growing, and they really press the one enzyme system and glycolysis for energy production. So ATP synthesis, heat, work, ion gradients, and so action potentials to get heart to work, the neurological responses that happen with contractions and exercise, active transport, so moving ions across a concentration gradient, substrate regeneration, so gluconeogenesis requires energy to basically take that pyruvate molecule and then move it up. Theoretically, it's not up, but visually it is. Glycolysis and remake a 6-carbon structure from 2 3-carbon structures. Tissue synthesis, and so protein synthesis, new proteins, tissue repair. So it's not necessarily tissue, but so enzymes, making new enzymes, making mitochondria. And so that's part of the adaptation process. The demand, so basically how fast is energy supply going to be, or slow? And it's due to, and from a sport perspective, the more actin myosin strands are interacted, the greater the demand. And so if it's a lightweight, there's less tissue being used, and so there'll be less energy demand. So the issue is intensity leads to energy demand. Why is that? Is because the actin myosin interactions, the skeletal muscle structures dictate it. And so, trying to think of an example. Well, when you adapt and get more quote unquote fit, there may be a situation in which actin myosin interactions may decrease because of the efficiency of the musculature. Oops, sorry. Should be neuromuscular junction. And will continue until fatigue or decreased volitional input. And so I think for everybody that's participated in sport, there's probably been some understanding of both of these. Biochemical fatigue, so the 400-meter dash is kind of the textbook example of it, where if you miss pace, especially if you put on more effort early, that fatigue is going to set in earlier. So if you don't pace well, you tend to succumb to this sooner than if you pace yourself well. And so, in essence, what you have is hydrogen ions or acid interacting with troponin and tropomyosin interactions. And so you have basically competition and disengagement of the contractile processes. And so going this actin-myosin interaction. So you get quote unquote acid disrupting that, the hydrogen ions from lactate, primarily in the case of the sprinting situation. And then you also have heat, acid, potentially kind of hydration status, regulating rate limiting enzymes. And so depending upon what's happening within the cell, the enzymes that are involved in glycolysis, beta oxidation, Krebs cycle, etc., are going to respond to that soup, if you will, the components that are within the muscle, whether they be lactate ions, calcium ions, whatever the case may be. Those things can regulate it. And then if you just, okay, I'm finished, and you volitionally, mentally stop wanting to produce power or as much power. And so you decrease the switch of, okay, I don't need to sprint anymore. That process will decrease the actin-myosin interactions. And thankfully, we're able to do it in a manner in which we don't stumble and fall until we get older, or some other neurological condition. So it's the body is adapted to where it knows how to slow down easily typically without injury. You can also have psychological fatigue in which you just, the wall sits, and it may be more, there could be some acid involved from lactic acid, but it just could be boredom. And you're just doing the same, walking, for example. It's not an issue of, you don't get much lactate. It's just, man, theoretically, it's a reason why a lot of people don't like endurance sports, like a marathon. You're doing the same thing over and over again. Swimming, that was my issue. Was the scenery doesn't really change much. You have a black line below you, and you just kind of stay on that for hours. And so there's a psychological component of kind of pushing through when you kind of want to stop. So the regulation, ADP, AMP are the precursors, or the substrate are the products of ATP catabolism. And so the rate of ADP and AMP production determines the rate of demand. And so it's kind of like exhaust in a car. The more exhaust you produce, the more energy you're using, kind of as the analogy. And so both increase when work is performed, serve to biochemically indicate energy demand. Same thing with NAD, NADH, which is the carrier of hydrogen ions for the mitochondria. When we get into supplements, these have become popular supplements in aging, sports, cognitive, the Joe Rogan type, Andrew Huberman supplement sphere, whatever dietary aspects of health and optimum performance cognitively, anyway. And so this ratio is an indicator of the rate. Lactate dehydrogenase gives hydrogen to pyruvate to make NAD available for glyceraldehyde 3-phosphate metabolism, for that step to continue in the cytosol. If this doesn't happen, if there's not a way to offload these hydrogen ions to the mitochondria, they will build up and these processes will stop. And so lactate dehydrogenase will need to make lactate instead of pyruvate in order to continue. And then that lactate, that hydrogen ion, will continue to increase to a concentration that inhibits work. And that's where you get the acidosis part and the burning sensation of doing work. And this is indicative, when this happens, it's indicative of there's some sort of bottleneck in the mitochondria, the electron transport chain, that is inhibiting the mitochondria. So it's either not enough enzymes, too much work to handle, for the mitochondria to handle it. Any of those things can be an issue. So the pathways should be review. One enzyme system, immediate system, ATP-CP. We'll get into this. So that's the reason for creatine loading, creatine monohydrate, glycolysis, glycogenolysis, anaerobic system. I don't like that term, but it's used. And then oxidative metabolism, the TCA cycle, respiration, electron transport chain of mitochondria. Intensity is dependent upon fiber types. So there is a genetic. This is where the genetics come in, where you can shift what you have to be more like a certain fiber type, but trying to make new is very difficult. So if you're born with a percentage, that kind of helps determine the sport you're going to be better at. Not saying that you will or you want to do that sport. That's also an issue, is you have to enjoy the sport that you're genetically have a genetic propensity to be better at. Pathway selection is really dependent upon fiber type recruitment. And then you'll have different enzyme concentrations and mitochondrial content. So on the slow side, slow twitch fibers tend to have more mitochondria or do have more mitochondria. You will also see them as red fibers versus white. And so this is kind of borne out in chicken, dark meat, white meat. White meat's fast twitch, red meat, dark meat is mitochondria. And so you look at the breast and the wing, I guess the breast in particular tends to be white meat, and the wings that need to be chronic work, legs and wings, the actual wings tend to be red or dark meat, slow twitch mitochondria. So just FYI, just if you hadn't heard that before, well, there you go. That's my limited. That may be the only thing you learn from your semester. Hopefully it's not, but it may be. So immediate ATP, CP. So this is the whole creatine issue, just making sure there's enough. One of the newer aspects, we'll get into this when we get into supplements and ergogenic aids, is the energy systems within the brain. Creatine seems to be one of those. And so that's why cognitively it can be beneficial for people that have issues with creatine intake. There's also the myokinase when it takes two ADP, so ADP being products of ATP. There's an enzyme that will bring those together, reform ATP, and so you can do these things quickly. The concentration of these enzymes, these kinase enzymes, is limited, and so you can't. That's the reason this energy system doesn't last very long. Whoa, shoot. Glycolysis. I think I'll just kind of go through these, and we'll get into more specific aspects of glycolysis and beta oxidation later. But just from a difference, faster rates of ATP or greater quantities of ATP, than the one enzyme system, not quite as fast, and yields a compound that can enter the oxidative metabolism system, biochemical regulator of intensity. And so you have acidosis that can occur if too much work too fast is happening. We'll get to more of this. We'll spend more time on this, but just kind of the regulation is AMP, ADP, and ATP. I guess maybe I should color these a different color because they do different things. The acid from lactic acid, or the lactate ion, hydrogen ion, citrate from the Krebs cycle, and then alanine is an amino acid, and it can, depending upon the concentration, shift the need for glycolysis, the rate of glycolysis. Oxidative metabolism is we get the greatest amount of ATP, but you can't, the intensity of that, there's a limit. Granted, when you train, you're training to increase oxidative metabolism. So even, team sports, you need to, it's one thing, so football, basketball, it's one thing to sprint down the court or to sprint down the field, but it's another thing to have that same intensity, that same velocity 20, 30, 40 minutes later. And so that's where oxidative metabolism can play a role. How quickly you can recover between plays is highly dependent upon your ability to tolerate the acid load and to manage the hydrogen ions that are within the system that have been produced from those sprints. See the same thing. So in hockey, I don't know how many follow hockey. Again, I'm a sports nerd, but you get line changes. And so there's a line change and they have fresher legs. So when one group switches, it gives the other group a chance to rest, recover, so that they can do more work. Skating, I don't know how many of you have ice skated at a quick rate or roller skated or rollerbladed. It's kind of like sprint cycling, and because it's all basing the legs, and then you have a lot of padding, a lot of weight from your equipment on, and so that's why trying to, and I don't know if any of you saw the movie, Miracle on Ice. I think that's what it was called. It was the ice hockey team from the '80 Olympics, I think, or '84. Gosh, I'm mad at myself for not remembering. I want to say '80s. But winter, because it was the Winter Olympics. I don't know if we competed in the Summer Olympics in 1980. I think that was the issue. We competed in the winter, but not the summer. Anyway, and we beat the U.S. And there were some exercises that they did to train for that, in which the coach, multiple sprints and just, I don't know what your coach called them, but basically line drills, infinite amounts. I'm not saying that wasn't infinite, but they were pretty severe and significant, just to get them ready so that they could do their line changes and with less time. So they didn't need to be pulled as soon to stay on the ice as long as they could, which is what you want, is to have your best players on the ice for as long as possible. And not saying that when you swap lines, you get decreased performance. However, the people who are starter, Wayne Gretzky, I'd want out there as long as I could, for example, for those that understand hockey. Let's see. We'll come back to that. Krebs cycle. So this is, probably have heard it. I do not require memorizing each step, each enzyme. However, it is an important process in which you're basically taking a 2-carbon compound, acetyl-CoA, and forming citrate, and then it comes around and you get back to a compound that can recycle. So it's not necessarily a circle, but there are compounds that will be used to just continue this process. And so there are enzymes at each of these steps to change the compound. And so you need citrate to move in this direction. And so each step requires a product and a substrate. And so as those products build up, so as citrate builds up, it's an indicator of, hey, we're doing work. I need the Krebs cycle enzymes to get up off the couch and start doing some work for me. As acetyl-CoA lessens, as citrate lessens, I guess we're not working as hard. We can take a few of the enzymes, can go back to the couch and get some rest. And so this is why protein intake's important, so you can have more Krebs cycle, TCA cycle enzymes, and just to build this process, if you want to train for aerobic metabolism or clearing lactate, clearing and using mitochondria to help with energy production, these are the enzymes that you want to use. You have, let's see, so part of the issues, you have water, CO2, here's your NAD, NADH, FAD, which is basically, it's similar to NAD, NADH, flavonine versus nicotinamide. And so you have these hydrogens that end up going into the electron. Those are the electrons within the electron transport chain. Just to kind of hopefully put some clarity. It's like, oh yeah, I remember that, hopefully. The other aspect here too is CO2. We'll get in, just remember where CO2 comes from. There's also CO2 that we get here, and we'll get to that when we get to, but the CO2, the carbon dioxide, is also important from metabolism. Let's see, anything different here? Yeah, CO2, guanidine. The GTP is basically, it's an ATP equivalent. This will get converted to ATP. And so while it's technically, this is usually a quote unquote trick question. How many ATP do you get with one turn of the Krebs cycle? Technically, the answer is 0, because you get the intermediates, the hydrogen ions, or the electrons, and a GTP. In essence, you get 11 ATP. And so I don't like that, but you may see this on some sports science thing where they're trying to trick people, and it's like, okay, yeah, you don't, but it doesn't matter. You end up with 11 ATP. That's the purpose of the electron transport, or the Krebs cycle, TCA cycle, whatever, is to generate ATP. So it's kind of a weird, I don't like that kind of question, but I get it, I understand it. It's kind of understanding the biochemistry involved. Sources: carbohydrates, lipids, amino acids, fates, lipid synthesis, we'll get to that when we get to lipids, and then ketones. Here's your ketogenesis for that type of diet. Let's see. So interaction of pathways. This is a very common graph. I hope you've seen it before. I think it's caused problems with other classes and how people think about the energy pathways. And so for sprints of 10 seconds or less, it is the ATP-CP, the long dash, and then which decreases over time. The solid line glycolysis, its highest rate typically is with 30 seconds to several minutes. And so I tend to use track and field just because it's an easier delineation. So you got your 100, 200 meters, 400, 800 meters, 1,000 meters, and then basically miles, 1,600 meters and on, all the way out to marathon. However, all of them are contributing. And so there's none that are fully 100%. And so that's the key thing to keep in mind is that, the flip side is, so when you get up and you go for a walk for 10 seconds, you're not using ATP-CP. The standing up process, you might use a little bit, but one way to kind of check is, are you breathing hard? So if you're not breathing hard, you're not really using any of these other systems. It's still oxidative metabolism. You have enough energy available. There may be some supportive use of glycolysis in the one enzyme system, again, to stabilize, to take those first steps, to break, but it's not a lot. I mean, it may be 30% of each when you walk versus almost 90% when you're competing in the Olympics at these distances, for these times. And to use team sports, it's going to vary. I'm trying to think of some examples. Soccer, it's going to be when you're sprinting to try to get a pass to score. And I'm sorry, I don't know the positions. It's the strikers. Sorry, soccer or football fans. It's usually whoever the fastest player on the team is with good foot skills, ball control skills, gets a lead out, and you try to get them the ball. When they're sprinting, they're in this category. For defenders, they're more in this mixed category of they may need to sprint and shift. And so with soccer, basketball, football, it's a constant shift of these energy systems. And so as the sport progresses, as the duration progresses and people get winded, that is, respiration goes up, all of a sudden you start to stress more of these systems. So it depends on, nothing against kickers in football. Their stress is mental. Physically, they'll do 5 seconds of the one enzyme system, maybe, just to get their leg to move as quickly as possible, and foot, the kicking foot. But there's not much other than that for some aspects. Archery, not much at all. It's almost all. There's some strength that's required to draw the bow, but other than that, it's concentration and oxidative metabolism. There's an example. I don't know if you've done a Wingate test. Maybe I think there's a video of it in one of the modules. I'll make sure that's available. Basically, it's 30-second sprint. Sucks. Did several of these. Not fun. And so you can't pace you are not supposed to pace yourself. So when you pace yourself, you're not doing it. You're not doing a Wingate test. The goal is to sprint all out. And so you can see that here, that you'll get fatigue, biochemical fatigue, creeping up as you get closer to 30. And then when you're ATP production, you're not turning the wheels the crank, this is a cycle ergometer, you're not cranking very fast. And so if you are cranking fast, you didn't do it right. And so what the goal is to see how much power and then what the trajectory of this line is. So it's kind of the power, you get a fatigue ratio and those types of things you can kind of get with that. But this kind of shows you, so one enzyme system continuously drops, and then glycolysis, it takes a bit to get warmed up, then it peaks, and then it also drops. And so so this light gray bar is a summation of both the ATP and glycolysis. Oxidative metabolism, really, unless somebody's really warmed up, there may be some of that in here, but for the most part, it's ATP, CP, the one enzyme system, and glycolysis, and they both end up dropping over time. And again, if you look at this, it's 0 to 1.5, 0, so it still contains, so it's not sequential. It doesn't get sequential until here. So 0 to 10, 10 to 20, 20 to 30. These initial ones, they're taking blood sample or muscle samples muscle biopsies at these time points to get the concentration and what the enzyme activity is of at each of those time points. So it's relative 1.5 seconds relative to 0, 2.5 seconds relative to 0, and 5 seconds relative to 0. And then you get 10, 20, and then you get 20 to 10, and then 20 to 30. So anyway, just to give an example of what that looks like. Talked about this. We'll come back to this. So increased enzyme activity, ADP concentration, increased ADP, NAD and NADH ratio, decreased enzyme activity is increased ATP. No demand. So you stopped. So you don't need energy. You cross the finish line. You don't need energy. You got fouled. You don't need energy. You just walk back to the free throw line or whatever, or get up off the floor. Might need some energy for that. Or inhibition. We'll get to these when we get into the specifics of it. Overall, there's a concept called anaplerosis. And this is where you get kind of the change in the soup concentration. And so you'll get ramping up of the TCA cycle, glycolysis, beta oxidation, and that it's the accrual of metabolic intermediates. So of citrate, of lactate, of any product that you need to do work outside of glucose and ATP. It's kind of everything in between there, and fatty acids and ATP. It's everything that you need to make that happen. And so this is where you also get fat burns in a carbohydrate flame. I'm not a fan of this concept. In essence, yes, energy has to start, ATP production has to start somewhere. And so that's kind of the basis of it. But once the wheel is in motion, it's not really. And plus, it puts a lot of emphasis on glucose or carbohydrate. And as we'll see, we technically don't need to eat carbohydrate. And so that's kind of where this also kind of gets confusing for some people. But it is a statement that you may see. So I'm presenting it just so that you kind of see it, hopefully in context. Hopefully my context is accurate. Let me know if not. And then beta oxidation, fatty acids. We'll get to this when we get to beta oxidation, but there's also an anaplerotic reaction within that because it's not a simple process either. So it's pre-Krebs cycle, much like glycolysis is pre-Krebs cycle. But so anyway, here's some review questions for you to look over. So you can pause it here. We'll talk about these later, but I just want you to have a chance to go through them. I'll talk about them with the on-campus class on Tuesday or Thursday, depending upon how far we get with that. But that's kind of just a basic introduction to kind of how I think, my perspective, my context on a lot of things. I tried to incorporate different sports and how energy requirements can differ with sport, which is different than, fitness and nutrition and exercise. Sport is completely different. Well, it's not completely different. It's different. And I just want to try to enhance and provide the sport aspects of this versus doing a resistance training workout, a treadmill workout, and what you would need to recover from just basic fitness or basic exercise. That's not what this is. And so we'll get into some of the specifics of this. When you have cross-country runners running 80 to 100 miles a week, you have basketball teams playing consecutively 4 days in a row, competing 4 days in a row, like what happens in the Big 12 tournament or postseason tournaments, and just the muscle damage, the soreness, muscle damage that happens. And the reason why you don't want to play through, just like baseball, same thing for pitchers in particular. The arm health becomes really important as the season goes along, and you get to a situation of needing arms to be as healthy as possible, and you may need to throw with a short rest period, depending upon type of pitcher, relief pitcher, whatever. Anyway, a bunch of different sports analogies. But there you go. End of kind of the first kind of lecture. Thank you. And I'll open up some discussion things or figure out a way to have discussions for this and so that there can be some communication if there's questions about certain things. So have a great week. Probably another video coming Thursday or Friday. I'm going to try to put 2 out a week. I'm debating the whole duration of videos. I'm still not sure how that's going to work. what's best. So you can drop that in the discussion. I think I have discussions open, but anyway, thank you and have a great first week.